All right. So we are currently studying limits and continuity. And today we're going to talk more about the second part, continuity. So let me just recap a bit the definition of a limit and how that changes when we talk about continuous functions. Okay, so the setup for both is the same. Let A be some subset of R, and say I have some function defined from A into R. So we call these functions real valued functions because they give you a real number. So this is the definition for a limit. Okay. An f be a real valued function. A be a limit point of the domain. So in order to talk about the limit, A needs to be a limit point of the domain, not necessarily belonging to the domain. Okay, so I'll put that up here, that A may or may not belong to the domain. Okay, so that's the main idea of a limit, that the point we are taking the limit as we approach, it may or may not belong to the domain. So A be a limit point of A. We say that L is the limit. Okay, of course, L is a real number. L is the limit of f of x as x approaches A if, so here's a definition. I'll call it to use green. If for any epsilon bigger than 0, there exists a delta also bigger than 0, such that if I take any point x belonging to A and the distance between this point and the number A is within delta, but I am not allowed to choose x equal A, so I put a 0 strictly less than, then the corresponding function values f of x is within an epsilon distance of L. Okay, so that is the definition of the limit. So how does that change when we go to talk about continuity? Continuity or continuous. So again, the setup is the same. So let A be a subset of R and F be a mapping from A to R. This time we're going to say let A belong to the domain. Right? So for the limit, A may or may not belong to the domain. If I want to talk about a function being continuous at a point, that point needs to belong to the domain. So let A belong to the domain, and we say that f is continuous at the point A. So when we talk about continuity, it's actually always with respect to a particular point. So f is continuous at A if, so now here's definition, and you'll see it's very close to the one for the limit. So if it starts off the same for any epsilon bigger than 0, there exists a delta bigger than 0, such that if I take any point belonging to the domain and that point, the distance between it and A is less than delta, and this time you are allowed to take x equal to A because A is a belongs to the domain, so f of A exists. Okay, this implies that the distance between the corresponding images f of x and f of A is within epsilon. So I want you to pay particular attention to how close these two definitions are in their setup and the subtle difference between them. Okay. Now, if it happens that this point A belongs to A and it is also a limit point, if f is continuous at A, then if f is continuous at A, then what ends up happening is the limit of f of x as x approaches A instead of it. So we know that this will be L, but what is L in this case? L in this case turns out just to be f of A. Okay, so this is the link between these two definitions. Right, so this is the link between these two definitions, is that if A belongs to A and A is also a limit point, then you could use the idea of the limit to deduce continuity. Okay, so the first thing we're going to talk about today is what if we do not have this case? So this case is if A is in the domain and it's a limit point. Okay, what if A is in the domain, but it is not a limit point? Okay, so we know that, let's recap this. If A is in the domain, then either A is a limit point or A is not a limit point, right? Those are the two options. If A is a limit point, we can check for continuity by, we could check for continuity by using is the limit as x approaches A of f of x equal to f of A, right? If A is not a limit point, then this is an isolated point. Isolated point of the set A. Okay, so if A belongs to the set and is not a limit point, then it is an isolated point of the domain. And remember what isolated point means. Let me just recap this. It means that there exists some radius. So let me not use epsilon. Let me use r instead. So we don't confuse it between the epsilon and deltas we already have. So there exists some radius r such that if I put a neighborhood around this point of that radius and I intersect it with the set A, there's only one point in that neighborhood. It's the center, A. In other words, it is if a point belongs to a set and it's an isolated point of that set, it means you could put a neighborhood around it that only contains one point of A, that point. Now, this is the same thing. If I now remove the center, So I take the deleted neighborhood instead. I intersect it with A, then that is the empty set. Okay, because if these two sets, the neighborhood and A, only have a single point in common, which is A, and I now remove A, then they have no points in common, so it's empty. Okay, so that is an isolated point. And what we're going to now prove is that if you are an isolated point, then you are always continuous. So that's the first thing we want to do today. Yeah. Okay, so that's given by the result of this theorem. So let A be a subset of R and F a mapping from A into R. So the setup is always the same. If A is an isolated point of the domain, then F is continuous at A. So all we have to do, so it's a sort of a weird thing. If the function is defined as an isolated point and there are no other points of A of the set around it, then you might think that the function is discontinuous because there's no other points around it, but it's actually continuous. And all we have to do now is check that this definition, this is the same definition of continuity that I wrote down. All we have to do is check that this definition is trivially satisfied, right? So we're going to show that this definition is satisfied within that neighborhood. Okay, so the proof begins by just writing down the definition of an isolated point. So let epsilon be bigger than 0. If A is an isolated point of the domain, then there exists some radius, delta, such that the deleted neighborhood around A of that radius intersect A is empty. In other words, there's only one point of the domain A in this neighborhood. It's A, it's the center. Okay, so now if I add back A into this intersection, then they only have one point in common. So the center is obviously in the neighborhood. Okay, the center always belongs to the neighborhood, and A belongs to the set A. Okay, where did I take this point? A is an isolated point of A means it needs to belong to the domain. So there's only one point in here. Hence, if X belongs to A, so what we're doing here is we are now going to check the definition of continuity. And remember the definition of continuity says, let epsilon be bigger than 0, then there exists a delta. Okay, so this is the particular delta I'm choosing. I'm choosing the delta that produces this neighborhood. So I need to check if I take any other point X belonging to A, and the distance between that point and A is within delta, then I need to show that the corresponding images, the modulus of f of x minus f of A, is less than epsilon. That is my target. But notice, if I take any point of A and within a distance delta of A, then that point must be in the delta neighborhood and belong to A. Okay, so what we have here is equivalent to that point being in this delta neighborhood, and remember intersection mean and belonging to A. But A was an isolated point, so we know there's only one point in this intersection. That is A. Again, there's only one point in this intersection. So X must be equal to that single point A, which means that when we work out what is f of x, there's only one value, f of A, which means that the distance between f of x and f of A, well, there's only one value of x I could possibly plug in here. That's A. So this number is going to just be 0. And obviously 0 is less than any epsilon you could come up with. Okay, so this here, this last part, this is the what we needed to prove for continuity. So you see, we always get continuity because the corresponding function values, so long as I stay within this particular delta neighborhood, the corresponding function values, the images of them, their distance is always 0 because there's only one value there. So this condition always holds. Therefore, f is continuous at A. Okay, so if A is an isolated point of the domain, the function is always continuous at that point. Now, it turns out just like with the limits where we have different or where we have a theorem that allows us to take the limits of more complicated functions, such as the product of functions, the sum, the quotient, multiplying the functions by a scalar. We have a very similar result for continuous functions. In fact, the proof of this follows from that one with limits. Okay, so this one is saying if I know two functions, so f and g are two functions defined on the same domain, and a is a common point to them. If these two functions, f and g, are continuous at this particular point, a, and k is some real number, then their sum is continuous at a. So another way that we say this is that the sum of a continuous function is a continuous function. If I multiply a continuous function by some number, by some scalar, then the resulting function is also continuous. Okay, so the multiple of a continuous function is continuous. The product of two continuous functions is also continuous. And the quotient of two continuous functions is also continuous, provided that the function in the denominator, when you plug a into it, it's not 0. Okay, so once we know f and g are continuous functions, we could build more complicated functions that are also continuous in this way. Right? And the proof is left for you to try. Like I said, the proof of this you can find pretty much in any textbook or easily on the internet, but you should sit and try it first. And it's very, very similar if you've done the proof for, so go back and check this section with limits, and you'll see a theorem very similar to this, but it has to deal with the limit, right? So using that, you could prove these. Now, with this theorem, we could show something like polynomials are continuous. Okay, so everyone here, I think, knows what a polynomial is. So a polynomial is a function from R to R of this particular form. Okay, so you'll know what a polynomial is. We're arguing here that all polynomial functions are continuous, right? Not only that, a rational function is just the ratio of two polynomials. So if you think back to your Calculus 1 and Calculus 2 course, when you all were taking limits of these functions, so rational functions, we had a polynomial in the numerator and in the denominator, okay? So it turns out that polynomials are continuous functions because they are built from continuous functions, right? The continuous functions that polynomials are built from is x. Okay, all I need to do is prove that x is a continuous function on the real numbers, and that's easy to prove. And once I could show x, so f of x equal x, the identity function, essentially. Once you prove that that is a continuous function, you are then going to use this theorem to build a polynomial. Okay, because what is a polynomial? So sub in instead of the function f and g, use x. So if x is continuous, then x plus x is continuous. Then any multiple of x is continuous. So 2x is continuous. 10x minus 10x is continuous. Then the product is continuous. So x by x squared is continuous. X cubed is continuous. X to the power of 100 is continuous. So you see, using these first three results, you could build anything that looks like this, a polynomial. And it's the same thing for the rational function, because once we showed that all polynomials are continuous on their domain, then I use the this fourth one. So if f and g are polynomials, then their ratio, which is a rational function, is also continuous, provided that the denominator is not zero. Right? So that's what a rational function is. So the domain of the rational function, where is this rational function possibly defined? The largest domain for a rational function is just the set of points in R, so all the real numbers, such that the denominator is not zero. Okay, so that's pretty clear. If you have a rational function of this point, of this form, where the numerator and the denominator are polynomials, then the largest domain you could define for this, so the largest set of points that could work, is just all the real numbers except where the denominator is zero. Okay, so that's the domain of it. And a corollary to that theorem is that every polynomial is continuous on any subset of R. So polynomials are continuous functions, and every rational function is also continuous on its domain. Okay, so the proof, like I said, it follows from the constant function, 1, and the identity function x being continuous on R. Because if I give you any polynomial, so pick your favorite polynomial, quadratic, cubic, 10th order polynomial, doesn't matter. Pick any polynomial. You can build it using two functions, 1 and x. And here's the thing, you are allowed to multiply these functions by numbers, multiply them by themselves, and add them or subtract them. Right? And you'll see that that's essentially what a polynomial is. It's just some combination of these two functions, which we know from that theorem. That's why this is a corollary of it. If 1 is continuous and x is continuous on all of the real numbers, then any sort of combination like that is also continuous. And in a slightly similar way, you could also show that the sine, cosine, hyperbolic, sine, hyperbolic, cosine, the exponential function are continuous. In fact, square root is also continuous. The logarithm, natural log are also continuous functions. So all of these you could show are continuous functions. The modulus as well is also continuous. Okay, so that's continuity. Right? It turns out that we can make let me go back to this. So we know that the sum, the product, the multiple of continuous functions are continuous functions. So let me see if I could come up with one. If I tell you, for example, so we know that let's say x squared And well, I just told you this, but we didn't prove it. Sine x is continuous on the real numbers, right? Y is, let me phrase it this way. Does this then imply that, so for example, using that term, then we could say that x squared sine x, right? Or uh, x squared on sine x. One sine x is not zero, or sine x on x squared, or any multiple of sine x times x squared, or x squared plus or minus sine x. All of these are continuous, right? We know that from that theorem. Is sine of x squared continuous? So now here's the problem. Yes, that theorem is very nice and useful because it allows us to multiply continuous functions, take their ratios, add them, subtract them, and you will be guaranteed a continuous function. Again, provided this guy is not zero. Okay, so you just remove those ones. But we cannot use that theorem to come up with a function like this, right? But notice that this function, sine of x squared, is simply if I call, for example, this guy f of x, this one g of x, notice, for example, that this is just the composition of g with f, right? So g composed with f. So what we're going to now show is that um, we also have another result, which is not only is the product of two continuous functions also continuous, but their composition is also continuous, which allows us to make even more complicated functions this way. Okay, so that's what we're going to now show. That the composition of continuous functions is continuous. So this one has a bit more setup to it. So let f be a mapping from A to R and G be a mapping from B to R, where B is contained in the range of A. Okay, so all that means, because we want to talk about composition, right? So here's A, here's R, and here's B. Okay, so F is a mapping from A into R. Okay, but remember, F may not be surjective, so it may not hit all of the real numbers. So let's say it only hits this amount, right? So here's F of A. You of course know that that is the range of F, right? So now on this range, we're going to call this guy sorry, B is in here. It's the next copy of R, right? So inside here, let me put F of A on the outside. A, then inside here, I'm going to put the set B. Okay. The reason why we need this sort of arrangement of the set is so that the composition would make sense. Okay, so now on B, I'm going to define a function G. Right, so again, the reason why we need this is so that the composition of G with F makes sense. Okay, because remember, what does this mean? G composed with F of X, it means that you first plug X into F, and then you plug that value into G. So this value here better be in the domain of G. In other words, this value here belongs to the range of F. So the range of F, which is this green set, oh, sorry, I had it. I drew. Yeah, yeah. Okay, no, sorry, your turn. Which is the range of f better be in the domain of G. Right, so you see, I had it wrong. So it's f of A. Yeah, so the range is in there. B is out here. Right? Okay, good. This one. Okay, so the range of f, whatever comes out from f, better be able to you better be able to plug that value into G, which means that the range of f better be in the domain of G, which is what this function is saying. So what we're going to show now is that if you take if f is continuous at some point x, I think they call it a. Right, so I stick to a. If f is continuous at this point, right, then this guy here is f of a, and if g is continuous, then the composition, which is this mapping, okay, so this is the composition mapping, is also continuous at a. Right? So it will map to this point here is G of f of a. Okay, so let's see how to prove this. So to prove this, all we basically have to do is write down the definition of continuity for f and g and then piece them together. Um, but in the previous proofs where we had more than one function and we were doing some proof involving limits or involving continuity, when we wrote down those two definitions, you see they were always defined on the same domain. In this case, we have f defined on the domain A and g is defined on a different domain, B. So we need some way to link those two domains together. Okay, so we'll see. Okay, so back to the statement, F is a mapping from A into R and G is a mapping from B into R, where B is contained in F of A, right? B is contained in F of A. If B is contained in F of A, what was B? I had it correct the first time then. The image um I think is F of A is contained in B. Because if B is inside F of B is contained in F of A, yeah, I had it correct the first time. I'm sorry about that. I had it correct the first time. B is supposed to be in F of A. That switches back again. Uh, so B is the innermost one. Right? B and then F of A. Right? The range is here. Yeah. So B is inside of F of A. Right? Because whatever comes out of F of A, oh, sorry, whatever comes out of F is in F of A, and that value better be in the domain of G, which is B. So B has to be inside. Yeah, so sorry about that. Okay, but it's minor technicality in the proof. So if now F is continuous at a point A and G is continuous at F of A, right, which is in B, f of a, which is a deleted. So here's f of a. Then the composition is also continuous, right? Okay, so let's see how to prove it. All right, so they had a drawing here, right? But their drawing is a bit complicated, right? It's the same drawing that I did. Okay, so the proof goes like this. So, like I said, we're going to write down the definition of continuity for each function, but we need to be able to link them. So first, we're going to start with G. So usually, or I think you might think that, okay, we're going to start with writing the definition of continuity of F and then go to G. But the thing about this proof, we need to start with the definition of continuity of G and then move back to F. So we start a little bit backwards. Okay, so we're going to start with the continuity of G. So since G is continuous at the point f of a, so think of f of a as just some point y or something, just some number in the domain of G. Then, so what is the definition of continuity? It means for any epsilon bigger than 0, there exists a delta. So instead of delta, we're going to use eta because we have to choose a delta later on. So eta is like an intermediate radius that we're going to use. So there exists an eta bigger than 0 such that um, if for any value y minus f of a less than eta and y belonging to the domain of G, the corresponding image of the function values is within epsilon. So even though this here looks a little bit different, it is the same definition of continuity. And only thing that we're changing is instead of x, we're just substituting it for y, but x and y, those are just variables, right? So using y instead of the set A, big A, we're using capital B, okay? And instead of the point being A, little a, the point you see here is usually modulus of x minus a, right? But instead of the point, we're using f of a because we are applying the definition of continuity between here and here, right? So we're linking these two. So you see that the points are g of f of a and f of a. And that y that you saw there is over here. So here's y, right? And here's f of y, sorry, g of y, uh, g of y, okay? That's how we got this definition. Now we're going to apply the definition of continuity for f. So we're using the same epsilon as before, but the delta or the second radius has to change. So since f is continuous at a, for this same epsilon, there exists a delta such that, okay, so now this definition should look familiar to you. This is the definition of continuity. Such that for x belonging to A and the modulus of x minus A is within delta, the corresponding image of these two values, f of A and f of x, the distance between them is less than. So usually we will put epsilon here, right? But we're going to we fix epsilon from the beginning, and that gives us an eta. So we're going to use eta over here. So those distances, those distances are here. So this distance is epsilon. This distance is eta, and a and here is f of x. This distance is delta. right? So when we're writing the definition of continuity for f, you see the distance we're working with is f of a, f of x minus a is within delta, but the corresponding image, which is f of a, and well, in this case, y will be equal to f of x, is eta, right? So once you have the picture, it's a bit easier to see which radius you are using. Okay, so we write the definition of continuity for both of them, and now we're just going to link them together. So what is the link between this? Well, I have an eta in the definition for G, definition of continuity for G. I have an eta here. I also have an eta here for the definition of continuity of F. So this first inequality holds whenever the distance between y and f of a is within eta. Um, but this second inequality holds when the distance between x and a is within delta. So if I choose an x value, right, within a delta distance of a, then that means that this holds. The corresponding f of x minus f of a is within eta. And if this holds, if this is within eta, that's the same condition as this one. So now this third inequality holds. So it's sort of like a transitive property propagating through the inequalities. Okay, so combining these inequalities, I'm taking y equal f of x gives, right? So uh, they are saying let's use the distance between x and a is within delta, and x belongs to a. So this inequality holds. If I now take y equal f of x, so in this first inequality, substitute for y f of x. Well, if you sub in y as f of x, then you get the modulus of f of x minus f of a is less than eta. But that's this inequality here. And this inequality holds because I chose x and a to be within a delta distance. So this first inequality holds, right? Therefore, I could remove these two inequalities, this one and this one, and simply say that as long as the distance between x and a is within delta, and I choose a point within a, then the second inequality holds, and the first inequality holds. Then that implies that g, so anyway you see y, replace it by f of x, g of f of x minus g of f of a, the distance between them is within epsilon. And what is g of f of x? That's the composition. G composed with f. And what is g of f of a? That's the composition. G composed with f evaluated at a. Okay, so these functions you see here are just the composition. So therefore, G composed with F is continuous at E. Okay, so that proof is a way to link these things together. Okay, let's see if I can try it. Yeah, so what I was saying there is if this is true, right? And this is true, right? So that's this and that's this condition. How do I get this condition? Well, if this guy is true and this guy is true, then that implies I get this. Okay? I'm saying that this, if I now let y equal f of x here, here, and here, then this condition is the same as this condition. So this one is true, Therefore, this condition is now true. And when this condition is true, I get this. Okay, so now what I'm going to do is I assume this condition is true. I'm going to now remove this one, and go straight to here. So this is true, means this is true. Right, so replace y as f of x. And this guy here is just g composed with f of x. And this one here is just g composed with f of a. Therefore, the function, so if you want to, you could replace this by h. Right, if you want to, you could replace it by h. Therefore, this is saying that the modulus of h of x minus h of a is within epsilon, which means h, which is g composed with f, is continuous. Okay, so once you have the picture and you write out the proof, maybe 2 or 3 times, it becomes clear how to do it. And again, what do we need to do this proof? All we needed for this proof, and even the previous theorems, well, we didn't prove those, but even to prove those previous results, all you need is the definition. That is why it's so important in this course to you need to know the definition, at least the definition by heart, because without knowing definitions, it's difficult to write any of these proofs.